Hello. I am back again with a new episode of Solid State Physics, and today we are going to continue the discussion that we had the previous week. Basically, we motivated what is the reciprocal space of a crystalline substance, and the reciprocal space that we defined was a very nice concept because what it does is basically it represents the periodicity of the reciprocal of the original lattice or the original crystal. So the reciprocal lattice or the reciprocal space can only be constructed because of the translational invariance or the periodic nature of the original crystal. So we saw that how periodic crystal ensures that most of the properties of the electrons which are related to the rho, or here I'm showing again just to have a little recap of the last session. So we are seeing that the rho or the electron density that has to be periodic because of the periodic nature of the crystal. So because of the rho r is a periodic function of position. So most of the properties that a crystal has or the substance has is dependent on the electron density. And also the nucleus is the positions of the nucleus that is also periodic. So if we say that the nucleus if there are some properties which are related to the nuclear properties, they are also going to be periodic. So in general, all of the wave functions, all of the properties, they are kind of periodic with a cell in a crystal. So um, if that is the case, then we discuss that how this periodicity can be leveraged to transform the function into something else. And we saw that what is discrete translational symmetry and how we can actually construct a Fourier transform of the function. Because of this periodicity, leveraging this periodicity, we can actually represent the function in another basis set. So if we consider the positional basis set as a basis set, so let's say it's a continuous basis set or it's a discrete basis set, where if the position is, let's say x equal to r, then this like one of the entries will be one. So it's basically like it's a infinite dimensional basis set. We are not going into that completely, but what I'm trying to say is the position can be thought of as a basis set, and we are transforming it to another basis set, which is called the Fourier set, Fourier basis, Fourier basis. In the case of crystal, this Fourier basis is what is called the reciprocal space. And from the Fourier transform, we saw that for 1D crystals, the what is the condition of the on the reciprocal vectors? They are that G into R has to be an integral multiple of 2 pi. And we tried to extend this into 3D space. And we got that the Fourier transform in the 3D space of some any function is given by this f of x equal to summation of g f of g f tilde of g e to the power g dot x, where g and x are both vectors. Okay, so now if we look at this and we want to see that what will be the condition for this to happen, we will see that g dot r has to be an integral multiple of 2 pi. So that is the main constraint to find what are the g's. So now we will find the g's of the reciprocal space for a 3D lattice vector, and we will actually see how to, let's say, how to calculate the different lattice vectors for different configuration of cells, how to calculate these things. So that we will do in some time. So let us first see how to calculate these g's. So let us say, um, okay, so g dot r has to be g dot r has to be an integral multiple of 2 pi. So r, as we know, that can be represented as r for where r stands at for any crystal or position of any crystal point that is given as a linear combination of, example, n1 a1 plus n2 m2 n2 a2 plus n3 a3, where a1 a2 a3 are what? the primitive lattice vectors. The primitive lattice vectors. Okay. So what I'm trying to say is that if you put that here, then what we will get n1 into a1 dot g plus n2 into a2 dot g plus n3 into a3 dot g equals to 2 pi n, an integral multiple of 2 pi. Okay, so if g is 0, obviously g is 0 is a solution here because that's a trivial solution. That's a trivial solution. Because if you put that, you will get 0 here, you will get 0 everywhere. So that is true. So we don't want to see these trivial solutions though. We want to see that, let's say n1, put n equals to 1, n2 equals to 1, n3 equals to 1. Okay. Or for example, let's say n1 equals to 1, n2 equals to 0, n3 equals to 0. This is another possibility. If we put that, what we will get is a1 dot g can be 2 pi n. So that is one of the solutions actually. So this n can be 0, this n can be 1, this n can be 2. Okay, so similarly, if we put this, actually, we will get that all of the g vectors will actually satisfy this 2 pi n a2 dot g equals to some 2 pi m, where m is some other k, where n, m, k are integers. So for all g vectors, all reciprocal vectors, all g vectors which are valid reciprocal vectors, the relation will be that a1 dot g equals to 2 pi n a2 dot g equals to 2 pi m a3 dot g equals to 2 pi k. So now let's see how to calculate these g vectors. Okay, so the g vectors, as we see that it's also a lattice, right? So the g vectors constitute a lattice. The g vectors actually must form something like this: m1 b1 plus m2 b2 plus m3 b3. All of the g vectors could have been represented like this. Could have been represented by this. These are the primitive lattice vectors of the reciprocal lattice. What are these? b1, b2, b3 are primitive lattice vectors of the reciprocal lattice. Okay, so that is a very good uh, thing that we can see here. Okay, so we put that here in these equations, let's say, and we get a1 dot p1 m1 plus m2 a1 dot b2 plus n3 a1 a1 dot b3 equal to 0 or 2 pi n. Same with the others. So why can't we construct something like, let's say, put these to be 0? So like we get some equation. It's basically like we uh, take three vectors and we transform them to another three vectors such that what will happen is a1 dot b1 is 2 pi, a1 dot b2 is 0, a1 dot b3 is also 0. So we are doing it like that. So basically what we are doing is, let's say we have one vector a1, one vector a2, and one vector A3, like let's say like this. These are the vectors. So they form a what? They form a cube parallelopiped. Um, Wait, we draw it properly. So it forms a parallelopipe like this. So there is not enough space, so let me actually erase it and draw in a smaller version. So yeah, let's say there is a unit vector, there is an unit vector, and let's say there is an unit vector. This is in a 3D space. So it makes what? It makes a parallelopiped. Okay. So this is A1, let's say. This is A2. This is A3. Now what we do is when we are intending to make a vector which will give dot product 0 with both A1 and A3, but it will give dot product 2 pi when it is multiplied with A2. So what we will do, we will take the perpendicular to A1 and A3 and we will name it, let's say B2. This is another vector. And we will choose the magnitude of this vector in such a way that when we dot it with A2, it gives us 2 pi. So if B1, if we take such vectors, so this is an idea, this is an ansatz kind of thing. So let's say we take B1, B2, B3, such that if we multiply the B1, B2, B3, so the rows are B1, B2, B3, the matrix, it's actually matrix with A1, A2, A3, where the columns are the vectors A1, A1, A2, A3, then we should get 2 pi into I, or the identity matrix. So basically, bi dot aj should be equal to delta ij into 2 pi. So if b1 and a2, if you multiply b1 and a2, I and j are different, you will get 0. But if you multiply the two same vectors, b1 and a1, then you will get 2 pi. And if we have b1, b2, b3 like that, you can prove easily that it will any g vectors which will be can be written as this will satisfy this condition. It will satisfy this condition for sure. So, okay, fine. So we want to make some B2. So how is B2? B2 is in the direction of A1 cross A3. B2 is in the direction, B2 is parallel to A1 cross A3. But we want a magnitude which is perpendicular to A2. So um, let's say we are taking A1 cross A3. Okay, A1 cross A3. So it has some magnitude. We would take the projection with dot product with A2. So it will give us some value. So let's say V. But we want to scale it such that it gives us 2 pi. So we will multiply it 2 pi by V to make it 2 pi. So it will be basically like 2 pi in pi V into A1 cross A3. That will be B2. And what is V? V is basically A2 into A1 cross A3. Okay, so this is done. So that is how we get B2. Basically, it is A1 cross A3, but scaled such a way such that when it is dotted with A2, it will give us 2 pi as an answer. So we get the primitive lattice vectors of the 3D cell. We obtain the primitive lattice vectors of the 3D cell. So 2 pi A2 into A3 divided by A1 dot A2 into A3, 2 pi A1 into A3, A2 dot A1 cross A3, 2 pi A2 cross A1 dot A3, A2 cross A1. Okay, so these are the primitive lattice vectors of the reciprocal space. So if you do G dot R, let us prove actually, let us verify. What is the G dot R? M1 B1 plus M2 B2 plus M3 B3 dot N1 A1 plus N2 A2 plus N3 A3. So if you multiply it, what you will get? You will get summation Ij Mi Nj a bi dot aj, right? It is in a compact form. So basically all of the mi ni, so it becomes m1 n1 b1 dot a1 plus m1 n2 b1 dot a2 and so on, so on. There will be how many terms? There will be 3 cross 3, 9 terms. But out of the 9 terms, 6 terms will have what? I not equal to j. So this will become 0. bi dot aj will be 0. So how what do we get? 2 pi summation ij mi nj delta ij, because we already discussed that bi dot aj equal to 2 pi delta ij. If I and j are different, it becomes 0. If I and j are same, it doesn't become 0, it becomes 1. So what it will become? 2 pi summation of I mi ni. This is what? This is and nothing but a some integer, because mi is also an integer, ni is also integer. So if you do mi, ni and sum over them, it's some integer. It will be 2 pi into some integer, it's capital N. So g dot r will always be 2 pi into some integer. So we proved that these b1, b2, b3, they form a set, a 3D set for a 3D basis, basically three bases for the whole, representing the whole 3D space, such that any vectors which are the linear combination of this will actually be giving us this perfect condition from which we can calculate the reciprocal lattice. Okay, so we will start to see what are the reciprocal lattices of some, let's say some vectors. So this was 3D. We can also do for 2D lattices. 2D lattice is easier. Why? Because we will do the same prescription. Let's say there is a 2D lattice. There is a 2D lattice. How will we do that? How will we construct the 3D one, the reciprocal one? We draw perpendicular to one of the lines, and then we take the dot product with this, so that it becomes 2 pi. So for a square it will become like this. Okay, for a rhombus, like looking like a rhombus lattice crystal, the reciprocal lattice will become this. This is the real lattice, this is the real lattice, and this is the reciprocal lattice. So in 2D it is very simple. So let us see some 3D lattice systems actually. Okay, some 3D lattice systems. We know very famous lattice systems: FCC, BCC, SC. Face-centered cubic, body-centered cubic, and simple cubic. So if you look at simple cubic, so let us start with simple cubic first. Simple cubic. What are the primitive lattice vectors of simple cubic? Pretty easy. Okay, this is a simple cubic. This is a simple cubic. This one. This is a simple cubic lattice. It doesn't look like a cubit, uh, but we can say. And this is also, let's say, let us draw the backside lines with blue color. Okay, so this is a simple cubic lattice. And what are the primitive lattice vectors? Pretty simpler. This will be just a x cap, a y cap, a z cap, or yeah. So a x cap, a y cap, a z cap. So these lattice vectors are already perpendicular to each other. So if we want to do that, if we want to do, let's say, B1, here A1 equal to AX cap, A2 equal to AY cap, A3 equal to AZ cap. So we actually have all the primitive lattice vectors. So B1 is what? 2 pi into A2 cross A3 divided by A1 dot A2 cross A3. You know what is the answer going to be because anyways they're perpendicular to begin with. So that will be 2 pi a square z cap because y cap cross z cap. So it will be x cap and a1 will be ax cap dot a square um, x cap. So x cap dot x cap 1, a square cancel will be 2 pi by a into x cap. So it will be parallel to the original vectors. So it will be, let's say, 2 pi by a. This will be b1, this will be b2, and this will be b3. 2 pi by a x cap, 2 pi by a y cap, 2 pi by a z cap. So if you Fourier transform the simple cubic lattice, it will remain a simple cubic lattice. Simple cubic lattice, if you do the reciprocal space, it will remain a simple cubic lattice. It will remain a simple cubic lattice. So pretty easy. Now we will move to more complicated systems, which are FCC and BCC. FCC, face centered cubic. So what is face centered cubic? So there's a cube. So I'm not going to exactly prove these things, but I am going to like leave it as a homework. So this is a, let's say, these are the points. So there are lattice points at every corner. So let us denote the backside also. Sorry. So let us denote the backside also. Yeah. So there are lattice points everywhere. This big lattice point we can't see from in front. And there are other lattice points which are in the face center, which are given as cross. And they meet at the center of the cube. Okay. So let's say these are the lattice vector. One in one way the not the basis vectors, but the lattice sides basically a1, a2, a3. Let's say this is a, this is a, this is a. So if we are supposed to now say like what is the what is the primitive lattice vector of this system? So we will see that the lattice vector, which is basically like um, the primitive lattice vectors, they are nothing but these vectors. They are nothing but these vectors. This is one, this is one, this is one. So they form a parallelepiped in which there is exactly one lattice cell. Because this in this cubic cell, how many cells, how many actual lattice points are there? So these lattice points are shared between 8 cubes, and these lattice points are 8 in number, so 8 into 1 by 8. But these green lattice points, they're shared only between 2 cubes, and they're in 6 in number. So that is 4. There are 4 lattice points into this cube. But primitive cell, if we say, primitive cell can only have one lattice point. It can't have multiple lattice points. So basically, the thing is um, that the if you see that the how the primitive lattice looks like, you can see this is the primitive lattice. The primitive lattice. This is the primitive lattice. So the drawing is pretty bad, but this is what the primitive lattice looks like. So mm, wait, I think the drawing is a little bit bad. So let me draw it again. But yeah, like you get the point that what the primitive lattice vectors are. Yeah. So mm, yeah, yes. Okay. So this is the primitive lattice vector. Here we can see there are 8 sides and there are 8 points at every side. So basically, so there is this point, there is this point, this point, this point, this point, this, 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 and also, yeah. So there is another point that is, yeah, this. So for by dark green, I am representing the points. So there are 8 points shared between 8 primitive cells. So there is only one lattice cell in this primitive cell. Okay, so the what are the primitive lattice vectors? The primitive lattice vectors are of the FCC unit cell are A1 equal to A by 2 x cap plus A by 2 y cap. The second lattice vector is A by 2 x cap plus A by 2 z cap. And the third lattice vector is A by 2 y cap plus A by 2 z cap. So these are the primitive lattice vectors. Now, if you put it in the formula and get B1, B2, B3, so what you will get, we will discuss next, actually. So we will discuss it next. It will discuss in some time. Before that, we will discuss the body-centered cubic because there is a very interesting relation between FCC and BCC in that sense. So, um, okay, so body-centered cubic. Body-centered cubic. Again, a cubic cell, and there are the back sides. But here, how many points are there? Here is 1 point, here is 1 point, here at the 8 corners, obviously. And there is another point which is at the center. Okay. So, what are the primitives, primitive unit vectors of this spell? these are nothing but, for example, so there is one which will join here to here. There is one which will join this to the orange point of the neighboring cell, and there will be another one which will join it to the another neighboring cell in the front, on the front of the. So these are the unit vectors, because if you actually look at these unit vectors, you'll see that they make a parallelepiped where in which there is only one lattice point. Otherwise, there are how many lattice points? There are two lattice points in PCC cell. 8 into 1 by 8, the red ones, and 1 from the center one. So 2. This is not a primitive cell. This cubic cell that we are seeing is not a primitive cell, but the parallelepiped which is created by this. So this goes here. So let us try to complete it. How does it look like? So this will be one phase. Then mm, this will be another phase. And so if you scroll up, and this will be another phase. Where there is another orange point actually here. There's another orange point here. So this is a parallelepiped of the BCC center, BCC unit cell. So out of them, so wait, let me complete it more. Hmm. Yeah, so this is also part of the unit cell. Okay, so these are the unit cells. These are the units. This is the unit cell, and out of them, we can see that the 4 points are actually the original points, which are where the at the corner, and 4 points are orange points, which are in the center. Okay, so there are only 8 points, and 8 into 1 by 8. So it is basically like one cell per unit cell, one lattice point per unit cell. So um, okay, so the lattice vectors will be in this case a by 2 x cap plus a by 2 y cap plus a by 2 z cap. A2 will be a by 2 x cap minus a by 2 x cap. Um, so minus a by 2 x cap plus a by 2 y cap plus a by 2 z cap, and A3 will be a by 2 x cap minus a by 2 y cap plus a by 2 z cap. For convenience, sometimes the convention becomes that this is minus. This is minus. Yeah. So this is a minus actually here. Okay. So makes sense. So basically, these are the unit vectors of the unit cell. And if we calculate B1, B2, B3 from this, you will see that they will form a FCC lattice. You can calculate, this is a homework, that calculate B1, B2, B3 from A1, A2, A3, just like we proved earlier. We proved it earlier, right? These are the formula for calculating the reciprocal lattice vectors from the original primitive lattice vectors. So if we say body centered cubic, and we will find that the reciprocal lattice will be FCC. So BC to reciprocal lattice will be FCC, and FCC to reciprocal lattice will be BCC. Very interesting phenomena. You can check it for yourself. Just put the primitive lattice vectors into the formula and see what happens. Okay. So the final one primitive unit cell is often called the HCP, or the hexagonal closed pack system. So the primitive lattice vectors are also, if we look at the primitive lattice vectors, then you will see that the primitive lattice vectors are this, this, and this. They make a parallel pipe. There is only one lattice cell. And if you Fourier transform it, and if you put it in the formula, you will get that HCP lattice will give you an HCP lattice. HCP gives you an HCP. HCP gives you an HCP. So it doesn't change. So what we found out that simple cubic remains simple cubic, FCC becomes BCC, BCC becomes FCC, HCP remains HCP. So these are the some of the key observations of the very conventional and very much used lattice or crystal systems that we know in nature. And in the next class, we are going to see that how this periodicity actually comes into play in electronic structures. Now we will actually move into from geometry. So we have finished the geometry. Now we will move to quantum mechanics. That how the quantum mechanical theories actually leverage this symmetry or translational invariance and this symmetry on the reciprocal space to formulate the problems and to simplify the problems. Okay, so meet you in the next class. Best of luck.